Hello there, physics students, and welcome back to another edition of Rapid Review for Honors Physics. Today I'm going to talk about conversion of energy, and that means we have to look at how to convert energy from one form to another and also understand the concept of efficiency in conversion. So, bunch of stuff we already know. We know work, power, energy. We know we can exchange kinetic energy for potential within mechanical energy, of course. We know a work energy principle, and we've done a lot of vocabulary, especially in this vertical direction here of mechanical energy and its various forms. Today I want to focus more horizontally in this picture and look at the various forms of energy, not just mechanical energy, but things like chemical energy and thermal energy and others. I just did a little brainstorm here, came up with a whole bunch. There are others. It's interesting to note that this energy is the same energy you've studied in physics class, in your chemistry class. Energy of joules that's the same joule in physics as it is in chemistry, as it is everywhere else. In fact, as you continue to study science, you'll realize there's a kind of a big unification of all the sciences when we begin to talk about energy, because it's universal. Okay, so a couple places, a couple ways we might convert energy. Couple quick examples, right? If you want to go from chemical energy to heat, you would use fire as a tool to do that. If you wanted to go from electrical to mechanical, you could do a motor. If you wanted to go from mechanical to electrical, you could use a generator. In fact, these are reverse processes of one another. You can actually use a motor as a generator, and you can use a generator as a motor if you just turn it around. So that's an interesting idea of how you can convert energy. Now, we can't create energy. It has to come from something else, right? Asterisk, when we start studying mass energy equivalence, we might want to put a little asterisk on that. But for the sake of this class, energy can neither be created nor destroyed. Okay, we'll use that as our foundation here. So you need a source of energy, right? Plug it into the wall maybe, or plug it into a charging station, right? Because you can take electrical energy from the power grid and at the charging station turn it into chemical energy in the car's battery, and then finally the battery can supply electrical energy to the motor, and you have the desired mechanical energy at the end that you were looking for, right? So in an electric car, there's a lot of conversions happening, right? And remember that that energy has to come from somewhere, right? Ultimately, at the beginning of that slide, you'll see it comes from the power grid, right? So the power grid, I took a couple pictures of the local charging station, right? It looks like this when you pull up to it, but of course, if you look in the background, you'll see where the electricity connects, and if you follow it up the utility pole and you look up, you'll see it connects to wires that go down the street and continue on to a source of power. More on that later. Okay, so it turns out that cars can only store energy. They can't create energy. So your electric car stores chemical energy in a battery, or a gasoline-powered car stores energy in the chemical energy of its gasoline fuel, right? You eventually run out if you burn up all your gasoline. A hybrid has a little way of taking some waste energy when you slow down. If I'm moving in a car and I'm slowing down, I'm losing kinetic energy naturally if I just coast. But also if I apply brakes, in most cars, traditional cars, the braking works by sucking away your kinetic energy and turning it into heat, which is wasted. Right? So the clever thing about a hybrid is it uses regenerative braking, and it converts my kinetic energy into stored energy in a battery, which I can later use, almost like an electric car would, precisely like an electric car would. I can take energy out of that battery, put it into a motor, and drive the car farther forward. Okay, that's a little bit about regenerative braking. I can't talk about energy conversion without talking about efficiency. It's a crucial element of energy conversion. Okay, take a look at this. The equation's pretty simple. Efficiency is just how much energy you get out over how much you put in. So you can never get out more than you put in, and therefore efficiency is always less than 100%. Think about that. It makes sense. So that's how things work, right? For efficiency, you may be surprised that your gasoline car, your engine, only is about 25% efficient. Okay? Most of the energy you get out of your fuel is wasted, and then there's a little misc. I don't know, maybe it's your headlights or your audio system or whatever. Okay? I got this information from a government website. You can check out that link if you're interested. I'll add that link to the notes in the YouTube presentation. Okay, here's another one. Light bulb. Oh, that's terrible. It's only 2% efficient. The rest is heat. Okay, so you get a little bit out and you lose a lot. Now that's for an old school light bulb. LED lights are better. You can look up their efficiency if you're interested in further study. So in review, we have made several points. We have said that there's many different forms of energy. We have said that we can't create energy. It has to come from something else. We can store it, and it's possible to convert, but you are stuck. You can never get out more than you put in. Another way of saying that is the efficiency is always less than 100%. Now, a little bit about electric cars. You may come in thinking, oh, they don't use energy because they use electricity. And now, of course, you know that the car uses electricity. It comes from the power grid, ultimately through that path we studied earlier. So you might want to know, where is that energy coming from? It's surprisingly easy or available. That information is pretty available. I'm going to show you a little link that I really like. If I want to know where my energy is coming from in the power grid, I can just ask the internet. There is an operator, there's a grid operator here in New England where I live. This is the northeastern part of the United States, and they serve the electric grid in a large collection of states here in the Northeast, and you can ask them in real time, like right now, I can tell you what they are burning for fuel, what they're using for fuel to create the electricity in this studio where I am currently recording, and for anybody else that's using electricity right now. Maybe they're charging their Tesla or whatever, okay? So check this out. So when I click on the link, I see in real time what we're getting right now to power our grid. Where I live at this moment, this is pretty typical. About 2/3 of it is natural gas. You can see there's other things providing power here too. Notably, renewables is about 10%. If I zoom in on that, you will see that of that 10%, about 2/3 is wind and solar. The rest is refuse, which means burning trash, and wood pulp, which is a byproduct usually of paper making or whatever. So you can see that at any one time, the mix of fuels just depends on what your grid operator is doing, and whatever mix they were doing when you charged your electric car, you are using those fuels to drive, with some, of course, efficiency along the way, right? So if your utility is burning coal to create energy, you are then, and you charge your car at that time, you're essentially driving a coal-burning car. So realize that any time that you use energy, it came from somewhere else, and it's always worthwhile to ask, where did that come from? Okay, so I think that's all I'll say today about energy conversion. Stay with us next time. There's more coming up soon.